everyone, and welcome to the Volta Foundation webinar series, where battery industry experts delve into trending topics. Today, we have an exciting speaker joining us, Bill Brown, Business Development Manager of e-mobility at Henkel Adhesive Technologies North America. Hey, Bill. I love your background.
Good morning, everyone. Thank
Happy
you.
to have you. Bill's here to share insights on material and application solutions to enable cell-to-pack battery design. My name is Myra, and I'm the Director of Member Success at Volta Foundation. Yeah, just echo Bill's sentiments. Thanks to everyone for joining in today. So, if this is your first time joining Volta Foundation program, welcome officially to the world's largest network of battery professionals globally. Our webinar series is one of about 15 programs organized by Volta Foundation, which is a nonprofit organization dedicated to supporting the growth of the battery industry. We've hosted over 40 in-person and virtual events just within this last year. It still is crazy to me. We produce industry-leading publications like the annual battery report. The next edition is ramping up right now. We have This Week in Batteries, Battery Bits. We focus on DEI efforts through our Women in Batteries program, as well as host the largest virtual battery career fair event within the industry. And everything we do is open access and centered on helping companies and professionals like Bill, like Henkel, like everyone in the audience today, connect, collaborate, and advance businesses and careers. So how do we make all of this happen? All of these incredible programs. I think Bill, and if we go to the next slide, we'll be able to see how we're powered at Volta Foundation. All of these programs wouldn't be possible without partners like Henkel and everyone on that list previously. So thank you guys for that. In addition to today's program, be sure to check out Battery Street, Volta Foundation Slack channel. Check out our YouTube channel. We'll have everything posted there. And subscribe to our newsletters, stay up to date on upcoming programs. And if you're attending the upcoming battery show in Detroit, definitely stop by the Volta Lounge, visit with us, connect with Volta Foundation. And there's a reception Wednesday night. And I think, Bill, you mentioned you're going to the happy hour as well, too. I saw that next slide. I love it.
Yeah, we have our booth as well. So we're at booth 2618, and we're going to have our full team there, and quite excited to meet you and many of the other industry professionals at the battery show in Detroit that's upcoming in a couple of weeks.
I love it. I love it. So Bill and I are hanging out at the battery show. Come hang out with us. And I mentioned Women in Batteries, and Henkel actually has Women Leading the Charge at Henkel program on Wednesday. So I'm really excited to hang out at your booth on Wednesday.
Yeah, it's going to
All
be a great
right.
opportunity. Really looking forward to it.
I love it.
Plus, I'll
Yes.
get a break
Okay.
from that session in the booth.
Right. Yeah, a little break. I like it. Perfect. Okay, we're familiar with Volta Foundation. We're making plans to party and connect at the battery show. Let's get everyone familiar with the platform before we start today's program. So if we just go to the next slide. Let's see. Yeah, perfect. All right. For everyone in the audience, on your screen in the upper right-hand corner, you should see three different sections. There's an icon with a question mark, an icon that looks like a little report, and then a little gear icon. So to ask questions throughout the program, if you hear something from Bill, you're really curious, just type it into the chat. And throughout the program, we'll see the questions come in. At the end of the session, Bill will come back on stage and answer all questions that we can from the audience. In the little icon that looks like a report with the paperclip, if you click that, there's handouts from Henkel for today's presentation that go a little bit into detail about what Bill will be talking about today. So that's there. And then there's a gear icon. If you have any technical issues, audio, video, well, I guess audience can't share their video, then you can click that gear icon for audio support, or you can put it in the chat, and a member of the Volta Foundation team will be in the background and hopefully can help you out. All right. We know about Volta. We're ready for the battery show. We're familiar with the platform. Bill, I'm ready to introduce you. Let's do it. So Bill Brown is joining us today, Business Development Manager for e-mobility at Henkel Adhesive Technologies North America. Bill's been with Henkel since 1997 and has a Bachelor's of Science in Chemical Engineering from Michigan State University. Prior to this role, he was Henkel's North America Manager of Application Engineering Group, responsible for product technical support, testing and validation, design consultation, implant startups, and troubleshooting. All right, Bill, I love it, the transition from technical to business. It's going to be a fun discussion. We're absolutely thrilled to have you here today. I'm going to hand it off to you.
Sounds great. Thank you, Myra. Really appreciate it. I'm going to go off camera because I don't think anybody needs to stare at me for an hour, at least during the presentation. So Myra and Volta, thank you very much for having the opportunity for us to present and share some of our technologies and information that we hear from the market. I'm quite excited to be here, and thank you to all the people attending today as well. So excited to share some of the technologies that we have and solutions that we think can help enable some of the next generation designs occurring within the battery electrification world, and quite excited to share some of that information with you today. So appreciate your attendance. Um, yeah, as mentioned, so basically the topic or what we're going to be covering today is really some of the material solutions that are going to be able to be used to enable some of the cell to pack designs for that. So um, really excited to share some of this. A lot of our focus that I work on is really focused around automotive or transportation, but clearly there's going to be a lot of applicability for some of these technologies and solutions into other markets as well. So moving forward, um, a little background on Henkel if people are unfamiliar with us. So we're a large specialty chemical company headquartered in Dusseldorf, Germany. So we have two different divisions. We have our adhesives technologies group, which I'm focused in on, and multiple business units focusing in on different markets within our adhesive technologies group. And then we also have our consumer brands division as well. So that's really going to be focused on home care, laundry care, and hair beauty care as well. So very diverse company. Globally, we're over 20 billion euro in sales, annual sales. So great part is very diverse company, a lot of opportunities, and really helps enable us for long-term success as a company. And we recently celebrated our 148th anniversary, actually yesterday, as a company. So great long-term success and great vision by our leadership group. Um, Getting into really some of our technologies that we provide to the electrification market today. So this gives a brief overview of some of the areas that we're focused in on as Henkel and our automotive group. So kind of a broad, diverse technology range of solutions that are used in today's electric vehicle designs. Some of these materials really can vary based upon cell type and then also module and or pack design. So we see some different needs and different technologies, whether it may be pouch cell, cylindrical cell, or prismatic cells, and then really kind of some of the designs from our customers and whether we're using some products, within cell, within module, or within pack. And today's talk is really going to focus or highlight three of our key technologies that really can help enable some of the next generation designs. We're really trying to look at that next design of cell to pack that really kind of simplifies the assembly process, reduces the overall number of components, and really helps kind of speed up production, lower the overall cost. But there's some challenges there on how do we make everything work. And that's where we're hoping to highlight some of the newer technologies that can help enable some of those design challenges and performance challenges. So with that, as far as just an introduction, there should be a poll that's popping up. We'd like to take a brief pause here and give you time to review the poll and provide some feedback as far as what you see as some of your biggest challenges as either design engineers or related to the market, related kind of moving from like a more modular design to a cell to pack design.
I love it, Bill. Looks like 50% of the audience think that everything, all of the above, are this is great. Good reason to have the discussion.
It looks like it. Yeah, we've got roughly 2/3 or a little over 2/3 now that have voted.
Yeah.
Um, and yeah, yeah, very interesting. But yeah, I would agree. I think, yeah, as you mentioned, Myra, a little over 50% mention all the or everything listed, right? Structural
Mm-hmm.
support, sealing, safety, increased risk of yeah, runaway are all factors, I think. Yeah. So all of above definitely was the highest, but I think also structural support and safety were kind of similar and close into second place at roughly 25% for each of those as well. So definitely some challenges that I think the market recognizes for that. So hopefully, yeah, very pertinent on that. So just kind of recapping, where we're going to be focused in on as far as just the battery cell into the pack design. As I mentioned right now, I think obviously there's a number of different designs being used. I think most commonly that we see, at least in production today, and kind of in some of the early first or second generation electric vehicles, is really where we're most commonly being used is a battery module that's integrated somehow into a battery pack. Often we're seeing more of a pack level cooling and some multiple levels of thermal management being used for that. But we're, as mentioned, really our focus is going to be on what are some of the options to really kind of create a high performance and continue with a low cost structural pack for that. All right, so kind of looking into the design, starting with yeah, kind of basics. Obviously, to have a structural pack, we're often seen using more of a rigid cell, right? I think we need materials that can help transfer or carry structural loads. So with that, we're seeing prismatic cells and cylindrical cells kind of being the predominant preference within the structural pack design for obvious reasons for that. Another trend that we're seeing is obviously larger cells as well, whether that be cylindrical cells or prismatic cells. Really, the goal there, obviously, you got more energy density within the cell itself, but if the number of parts being assembled together can be reduced, it's going to be a slightly simpler manufacturing process as far as combining the number of components together and really handling those materials. So seeing a few trends related to these, yeah, the cell types as well. So really some of the benefits of the cell to pack design as far as, the market interest, really, again, it comes down to simplification, right? If I can reduce the number of parts, reduce kind of from a, eliminate at least module concept, or at least limit or reduce the number of modules being used, the overall assembly process is really going to be simplified, which helps reduce parts. And then also, if you're eliminating some of the additional components, obviously there's some cost and also potential weight savings for that, which then can obviously help with the range of the vehicle as well. So really, a number of factors related to performance and cost are driving this design preference. With that, obviously, there's some challenges, which the poll also kind of highlighted as well. But now that we're utilizing most of the space for cells, there may be a loss or limit of how do we maintain that structural support, and then also related to safety. Right now, there's a lot of cross members within the battery tray structure itself. They provide some of the obviously structural support, but also can provide some of the isolation between, say, the module bays. Um, but now if those are eliminated, how can we manage some of the structural loads and really safety aspect for that? So definitely some challenges on moving to a full cell to pack design there. So the first technology that we want to highlight right now, I think there's, again, a few different designs that I mentioned out there, but what we want to talk about is our thermally conductive adhesives. So within, there's a number of pack designs that are really using like a pack level cold plate um, currently. And so then there may be multiple layers of TIM material, thermal interface materials. You may have a material used within the module assembly itself, and then often there's going to be what we call a thermal gap filler, but really it's kind of more of a low strength serviceable type of material that would have thermal conductivity capabilities that would be used between the module and a pack level cold plate. Um, so obviously with a structural design, we would remove that serviceable or low strength thermal gap filler layer and really try to create a structural bond between those. So the Yeah, so the idea of a thermally conductive adhesive, for those who may not be familiar with it, the real benefit is now instead of one product doing one function, we have one material doing a dual function where we're helping manage or transfer the thermal conductivity. Um, but then also carry some mechanical loads or structural loads within the material. So you get the benefit of having one material or one product doing multiple functions, which is always a nice engineering benefit and also cost benefit associated um, with that type of material. So the concept or challenge then is how do we pick the right material for that? So when we start looking at thermally conductive adhesives or thermal interface materials, there's really three performance characteristics that we really want to focus in on. One obviously is the thermal conductivity performance, the thermal performance of the material. So often we're looking at bulk thermal conductivity number, but as all the design engineers know, it's really about how do we really try to minimize the thermal resistance of our interface as well. So we're looking at thermal conductivity requirements in the materials. We would look at any kind of electrical or really more accurately, probably dielectric performance in the material. If there's a certain, do we
Uh,
lose?
The, we may have lost the slides. I was going to
Okay,
play the
sorry.
video for you for step
I
one.
was
It's such a
wondering if
cool
something
video, but I
happened.
think I
I
think it closed your slides.
did it. Let me
Um,
try to reshare. Sorry about that. Did
yeah,
that,
no, I
is
think
it
it was
back
my
now?
fault. I
How long has this
apologize.
been
I
out?
think that was my user error. It was just when I tried to play the video. So I'm happy to play the
Oh,
video to set the stage for this part if you'd like. It's such
okay.
a cool video. You want me
All
to
right.
give it a
Yeah.
try? Okay. All right. Nice. All right, now you'll just have to bring your slides back
All
up. I love that video. Thanks, Bill. Sorry I interrupted
right.
your
No, no,
flow.
that's good. I appreciate that. Let me, all right. Should be coming back now. Yeah, no, that was a nice video just kind of showing the ease of automation for these materials. And we'll talk about a little bit about the application side of those. But yeah, the idea is definitely a material that can be highly automated for high volume production. So that's definitely, that would be kind of the fourth bucket of goals for these materials as well. So I mentioned thermal performance, was talking about dielectric performance. If there is making sure um, if that property would be important. And then again, going back to the dual function of these materials, we'd be looking at the mechanical performance of these products. So we'd be looking at really the substrates to be bonded. Are we bonding to aluminum, some type of coating, or exactly what we'd want, or the substrates that would be used with the thermally conductive adhesive, and then some of the mechanical strength. So are there certain tensile strength or modulus, elongation, and different mechanical properties that would be targeted for these types of products. So we'd want to understand that. And then the fourth leg that's often not looked at early on, but we definitely want to consider that, would be more of the manufacturing or processing side. So ease of automation, your tack times and volumes needed to make sure that we can dispense enough material within your desired cycle times, and then really looking at if there's a targeted cure rate as far as fixture time where the adhesive starts structuring to create some mechanical strength to help carry loads as the packet moves down the line. So it's kind of a trade-off on what we'd call open time, where basically you have time to assemble the components together and still achieve a very high strength durable bond. And then kind of as it moves down the line, we want to make sure that it cures enough to help carry any loads or handle any kind of part transfer throughout the process. So definitely want to consider manufacturing or processing of these materials as well. Another area that really looking to, speed the design and validation is how, um, our customers can use simulation, and really then how can Henkel support the use of simulation to, one, kind of validate or define the properties needed for these materials, but then also prove out their performance. Obviously, the use of CAE is going to help our customers lower their development cost and also significantly speed up their development timelines. So we definitely are investing the resources to help our customers with that, either through testing or similar kind of mirrored simulations to ensure that we can look at it through our team, along with the customers looking at it through their teams, and kind of validating designs or assumptions, or providing guidance on how to model adhesives, because I think there's some challenges or limited experience with that, and we want to make sure that our customers are using our data properly to get true results out of their models. So some of the areas that we're investing in and our customers are looking at would be CFD. So that'd be kind of a compression force look. So really it's looking at the forces needed to spread our adhesives out, and really kind of the coverage of liquids over gaps, and just ensuring that we're not imparting high forces into some sensitive components as well. Obviously, the more traditional mechanical modeling as well, that we can provide some material cards or test data to assist through the mechanical modeling, and then obviously the thermal modeling as well, just ensuring that with the thermal conductivity and managing all the thermal aspects of the design, that again we could provide some data related to the thermal model as well. So we see modeling and development for those three key areas as highly important, both for us and for our customers. Looking kind of more specific within the TCA, thermally conductive adhesive portfolio, definitely we see that we're often customizing these materials based on a lot of the requirements that I've mentioned over the last few minutes, really looking at performance on the thermal, mechanical, and electrical properties, optimizing different factors like density, just to help ensure that we're reducing weight as much as possible within the pack, optimizing key processing or manufacturing characteristics, and then just ensuring volume and cost targets are achieved for customers' unique applications. And then talking about application, there's a few different kind of rheological properties that we can hit as well. So some customers may prefer a high viscosity non-sag material, and others may want more of a lower viscosity or kind of an injectable type process or lower viscosity material for lower force and lower wet or ease of wet out as well. So definitely some varying properties that our experienced product development team is well aware of and have developed some quite amazing products for this market over the last number of years for that. So thermal management, thermally conductive adhesives is one challenge. I think one of the greatest challenges I see is really looking at the electrical insurance or electrical isolation within the design, which is definitely a key aspect of safety. So um, often either cells or the cold plates are going to be wrapped, or the use of a PET or some type of isolation foil. The challenge with that is often that foil or wrap is going to have low adhesion to the substrate that is applied to, or at least limited adhesion. um, I'm always big in analogy, so I kind of equate it to putting mayonnaise within a sandwich. So no matter how strong the sandwich is, if you have one layer that's kind of weak or slippery, that's really where you're going to have your limitations on strength. So if the PET sticks to the cell at say 2 megapascals and my thermally conductive adhesive is at 10, I'm still going to always have that limit of that 2 as kind of the weakest interfacial layer. So we need to find a different way or different method to ensure that electrical isolation um, for safety reasons, but create a much higher adhesion to either the cell or cold plate. So then we can really maximize the strength or benefits of the thermally conductive adhesives that we previously discussed. Um, So yeah, kind of covered a lot of those key areas, but really are technology focused and have some really nice products for this. Would be kind of more of a chemical or liquid applied dielectric coating. So very automatable, high volume spray. Need to ensure consistent thickness for your dielectric resistance, but then kind of equated. It's not an adhesive, but it has like adhesive or paint type properties where the adhesion to the substrate that we're applying to is very key in order to remove that mayonnaise layer and create high adhesion, right? So now we have, at least in the image here, we would have our cell, our coating that's applied and would have very high adhesion to the cell can, and then the thermally conductive adhesive would create high bond strength to this coating and then to the yeah, additional substrate to help carry the structural load within that design. Um, so,
Bill, also don't want to interrupt your
yeah,
flow, but there is a cool animation of this as
all right,
well. If you wanted to
yeah.
share it before or after this section, just give me the green light.
Um, let's do it right now.
All right. Dielectric coating application.
All right,
Those animations are so great. You'll just have to reshare your slides.
all right.
It's so disruptive to your presentation. I'm sorry,
No, it works
but I
out well.
love them.
I'm yeah. getting well trained on making sure I'm sharing the presentation. So very good. Yeah, so this would be just kind of a graphical or image representation of what I described, right, where you'd have your dielectric coating with your thermally conductive adhesive bonding to it, and then in this case, the cooling plate as an example um, for that. So really kind of how these are used or how we're formulating and designing really kind of the benefits here. Um, so you mentioned automated, typically some spray application, but we're really trying to put some unique functionality into these coatings besides just you know, coating or isolation layer. So we're trying to ensure high dielectric capabilities for that. We're adding some, I'd call it limited, but the products do have some thermal conductivity to them. And then we're also trying to optimize the coating thickness to keep that as thin as possible. So again, I mentioned that really it's all about thermal resistance, not really the bulk thermal conductivity of the materials. So if I have a thin coating layer with thermal conductivity. And then we have our thermally conductive adhesive. We're really trying to optimize or reduce that whole thermal resistance stack up within the design that really then helps optimize or creates the most efficient thermal transfer between cells and cold plate or cell and cooling structures for that. So, and then from the process, I mentioned spray, but really what we're looking at, kind of from a, whole market and corporate standpoint is, um, sustainable types of technologies. So this would be cured with UV. So what we're doing is eliminating any kind of heat or oven cure. So we can, and then also these would be compatible with LED curing systems. So we can really reduce the overall process time um, from application and then cure. So the footprint for curing equipment within the plants would be greatly reduced. Reduce the work in process, number of parts within the whole process, and then also lower utilities. So we're able to maximize the footprint, manufacturing footprint within the plants and reduce the overall operational cost associated with these technologies. Some really great benefits from an application standpoint with the UV curable or light cure coatings. And then also obviously the benefit to help enable the structural design for that as well. All right. And then the last technology that we want to highlight would be structural adhesives, right? So maybe we have large modules or packs, but then how do we really help use structural adhesives to help kind of transfer, carry all the design loads for that versus some traditional joining methods? So I think there's a video in here as well. Um, so again, can structural adhesives replace some traditional joining methods or help augment traditional joining methods to really help with that whole structural design? So the video shows more of a module to pack design, um, but again, we could use structural adhesives for multiple different applications. Um, so the benefits of so this would be kind of creating some of the cross-member, more modular designs again, and then obviously some sealers or some other products could be used to ensure isolation and water safety there. All right. So benefits of structural adhesives. Obviously, everybody's aware of kind of traditional mechanical joining, whether it be some kind of fasteners or rivets or welds, and they definitely have their place. But the benefits of adhesives is we're really able to utilize that entire surface area or coverage to help carry or transfer loads. Obviously, depending upon the components, but definitely some components within the battery packs are not compatible to traditional joining methods. And then also joining to similar substrates. So we're seeing a number of different, obviously, metals, coatings, plastics, or composites being used within these designs. So by the selection of the right structural adhesive, we can find a material that can bond to both substrates and really help kind of carry or transfer some of those loads through that. And then, yeah, then the materials themselves can either, similar to the thermally conductive adhesives, have different mechanical or elongation properties to then really kind of optimize that, whether we need to absorb some, vibration or loads or have a really high strength material for that um, for the application of that. So we have three kind of core chemistries that we would lump into or bucket into structural adhesive category. They would be epoxies, polyurethanes, and acrylic adhesives. They all basically have their different benefits and strengths. So epoxies are typically used in metal bonding. So they're typically going to be the highest strength structural adhesives available. Depending upon their formulation, they may have some limited flexibility or fracture toughness. Are going to be typically your hardest, most rigid materials, but definitely can carry very high strengths and good bonding properties for that. Acrylics are a nice chemistry as well. They kind of give a nice blend of metal and or plastic and composite adhesion. Um, can cure quite rapidly at room temperature and then also can have some improved toughness or flexibility compared to epoxy systems typically. The challenge is that often the acrylic systems would be considered flammable and do have a odor associated with that. So some companies may prefer to avoid this chemistry due to those characteristics. Others definitely use them and manage it. So it's kind of a um, mixed reception to the market with these materials. But there's definitely ways to manage these products from both a flammability, grounding aspect, and then also some ventilation to help with the odor, just so the operators or workers don't aren't affected by that at all. And then the last chemistry would be polyurethanes. So these are probably the chemistry that we see utilized most frequently, but they can definitely be formulated to have some unique benefits, either very high strength, rigid materials, or a little more elastomeric, lower strength, higher flexibility for that. Again, they bond plastics, composites, e-coats well. Sometimes they have had limited adhesion to, say, bare metals, but there's definitely some advancements that we've been able to make to increase adhesion to bare metals with the polyurethanes without needing a primer or some other systems for that. But it's definitely something that we'd want to or recommend customers engage with us early on, just so we can ensure that we're creating high adhesion within those substrates. So now we have different solutions that can create very high strength bonds within the cell pack. That often leads into one question from our customers of, gee, if we want to do some in-cell or in-plant repair due to some issue, our final assembly has significant cost to it. But if we're so strong and have created such durable bonds, how do we get things apart for repair to help limit our or increase our yield and limit our scrap cost, or end of life, or even, well, more in Europe, but seeing it in other areas as well, either consumer right to repair, or end of life and ensuring kind of full circularity within the market. How do we get things apart? So that's definitely a challenge, but heard it loud and well from the market, and that's been an area that we've been investigating and working on for the last few years on how can we create debond systems after we create bonds that perform very well for the life of the component. So there's a few different ways that within the market that there could be debonding or separation of these materials. So one obviously would be mechanical. That's going to be obviously limiting with the high strength materials. Another one would be chemical, but just looking at it from a green or sustainability aspect, that's a path that Henkel's chose not to pursue. So our focus, which is shown here, has really been on two different trigger systems. The first one would be a thermal trigger, and then our second pathway would be what we call EDL, or electrical delamination. So these different products definitely would be more designed in than kind of a drop in, but we're seeing interest throughout the market for different joining areas within either, say, module or pack designs, and definitely applicable into other markets as well. For some type of debonding type of mechanism, or debonding adhesive, or thermally conductive adhesive. So jumping in just into some brief detail with the thermal trigger. So this would use kind of a additional interfacial layer that would not impact on anything within the structural stack up of the bond, but with low level heat. And this can be customized depending upon the operating range of the actual application, because obviously we'll want the trigger to occur well beyond the standard application operating range for this. Um, but in this case, we, at least in the demo, show a prismatic cell where we heat it up very quickly. The temperature within the cell stays below its kind of safe operating temperature, but then the thermal trigger interfacial layer is triggered for ease of separation between the different components shown there. So again, create a very high strength bond, but then easy manual separation with this. And similar with the EDL as well. So a few different techniques that can be used. Um, but if we have two conductive substrates, we would then apply voltage to the substrates, and then with a short period of time, we basically get a diffusion of ions to the different surfaces that creates a very weak boundary layer. So then the adhesive can be basically peeled right off of both substrates that create a very clean bond on the two components. So carried out at room temperature. Time can vary depending upon the voltage, but a pretty quick process to create the delamination and very clean separation that would then allow for the components either to enter the um, you know, second life recycle stream, or be reworked into a new part to address the whatever issue that was creating for the rework that was needed. So with that, we're at the end of our talk today. So we do have one final poll. Um, so it would be basically some feedback on applicability or interest within some of the technologies. So if you could um, answer, yeah, 1, 2, or 3, we'd appreciate feedback, and definitely would be willing or high interest to continue the conversations on a one-to-one basis for each individual applications or needs. So I see the volts coming in, so really appreciate everybody's feedback or selection on this. All right. think we're ready to move on. So mentioned our battery show. So just as a reminder, um, we'll be at the Detroit Battery Show. It's occurring from October 8th to 10th. Our booth is 2618. Um, on the left-hand image is our what we call our Battery Engineering Center, which is located currently at our ICD, our headquarters in Dusseldorf. So it's a great dedicated lab and resource um, for the development and advancement of battery technologies, and we'll be replicating this type of capability in our North American automotive headquarters located in Madison Heights, Michigan as well. So that's going to be one of our areas of highlight at the battery show, along with some additional technologies as well. So hope to see everyone there. And with that, I think we're ready for the Q&A.